Thanks for attending this webinar series. My name is Tony Holmes. I'm the Applications Engineering Manager. Today we're going to talk about return path monitoring and maintenance. You'll notice on the screen that there's a chat feature that any questions that you have throughout this webinar, feel free to send a chat question via the chat, and that will come directly to me. And at the end of the webinar presentation, I'll address the chatted questions that were sent. So, as a webinar outline, there's actually a lot of things to consider when we're talking about return path monitoring. Things that's sometimes taken for granted. One is just the tools that's used and how to use it and who should use it. So this is going to actually cover a lot of those aspects. We're going to talk about return path certification. This is going to be more for what the field techs are going to need to do, but now the monitoring software is going to steer them the right direction as far as verifying if the area that they're actually certifying that it is cleaned up, but then also when they have to do any recertifications on that particular return path, that it gives history and it gives them a targeted area of which path to certify first. We're going to talk about return monitoring. Within return monitoring, we're going to talk about DSP technology advantages, what some of the advantages of DSP. We'll talk about how to prepare for return path monitoring, how to prepare for it. And then we'll go into managing the alarms that are sent back. We'll talk about generating the reports. And then we'll also talk about creating and viewing historical data. So let's go through it. Let's first talk about return path certification. Now, with certifying the return path, and there's so many different methods of certifying return path, or what's considered that your path is actually certified. Some examples, some systems will do a 1 hour max hold on the return trace. If you're looking from 5 to 42 megahertz, you would set your spectrum analyzer to look at that particular node, all of the return energy that's coming back to the head end, and just do a max hold on that particular spectrum, and within that 1 hour period, and then you take a snapshot after that, and if it's below what you're considering to be your system's threshold of Ingress, then you consider it certified. Some will do it for 10 minutes. They just go and look at the return path for 10 minutes, and if there's not any ingress that's coming in that particular period of time, then they consider it certified. The results are considered to demonstrate that over this period, the network would either pass or fail based on the amount of ingress that's viewed, how much what I consider garbage that's coming back on the return path. See, but the thing is, voice over IP and even just high-speed data in general, since there's businesses, commercial businesses that use the high-speed data, and like I said, the voice over IP, it is not a 1 hour service. It's 24/7. This maximum measurement is also not indicative of the true performance of the network. The certification process should be at least, and this is at least, 24-hour certification. And it should be an ongoing figure of merit. So the thing is that the proper way, or the way to get the best indication of how your return is going to perform, is actually looking at that return path for at least a 24-hour period. Because the thing is that let's say if you only checked it between, you did it for an hour at 9 o'clock. 9 o'clock a.m. you go in and do the certification. But now, what happens that if there's a machine shop that's in the area, and they actually start doing all of their machine work, or they turn on a particular drill press or what have you at noon, and that's the time that they use it, from noon until 5 o'clock is the only time they use that. But whenever they turn it on, it causes distortions, or causes ingress on the plant. Or another example would be if a homeowner gets home and they get home at, we'll say, 6 o'clock, and every time they turn on a particular on their stove, that maybe there's some electrical impulses that's coming off of that particular stove that's migrating onto the return path through the cable system that's inside of the house. So it's important that it's not just looked at in a 1 hour period or a 10-minute interval, that it's important that you actually look at it for a 24-hour period. And it's really should even go further than that. It should be a continued check over that over the 7-day period, because there's sometimes that you'll have more problems on the weekend than you have during the day or during the weekday. So as a troubleshooting summary, now let's say that you go through and check your notes, or you're doing the certification and there are issues. What you want to do is first verify at the node. Determine which legs are contributing to the problem. So using your analyzer, since you already know that the composite noise that's coming back to the head end exceeds what you're considering to be your minimum tolerance, then just check the individual legs that are coming back to the node and see which one is causing you the most problems. And then identify the span using the amplifier test points. And you want to get ahead of the problem. You want to identify which particular leg is having a problem. So remember, we talk a lot of times. You've heard this so many times. The divide and conquer. That's what you're going to want to do. And then isolate to the particular tap. Using a return path test probes, you can isolate the problems using the I-stop filters. You could, which is, if you're not familiar with the I-stop, that allows you to plug in a test probe into your KS port, or where your seizure screw is on your tap. You screw that into there, and by pressing a button, it loads down the return. Now, the customers don't see this, but it loads down the return from 3 to 6 dB. And if you see the levels drop by that particular amount, then you know the problem is further downstream from you. If you press the button and it does not make a change, then you know the problem is further upstream. The I-stop probe is a Trilithic probe, and you can contact us for more information on that. But it is a very useful tool when you're doing your return path certification. And then you want to pinpoint the origin to a tap or a damaged cable. You'll find that most of the problems that you have are going to come right from the customer's house. I mean, about 90% of the ingress that comes back onto the return path comes right from the customer's house, or the drop or the tap right in that area there is where you're going to have most of your problems. See, but what makes this a little trickier is it's not necessarily just that one house that could be causing the problems in the nodes, because when you talk about return, and we talked about this in one of our other series, is it's a funneling effect. So the composite of all of the nodes that are combined, or all of the test points and taps and line extenders, everything that's combined to that particular node, the composite of that energy is going to affect the overall return path. So now I mentioned using DSP technology, and that's digital signal processing. Let's talk a little bit about that, because one of the things that that I see systems struggle with is that there's a quick impulse noise that comes in and goes, and sometimes their analyzers don't see it. Because the thing about analyzers, there's two types of analyzers. There's the swept-tuned analyzers, and then there's the analyzers that uses digital signal processing. Now, Trilithic uses digital signal processing. The thing about swept-tuned analyzers, there's a sweep pulse that runs through the frequency spectrum, and if there's some ingress that comes in where the sweep pulse is not presently at, then it will miss it. So the likelihood of you catching real fast transients gets a little slim. So the advantages of DSP: it provides the fastest method of measuring return path ingress levels, because it's actually taking a snapshot digitally, and it's mathematically displaying the results. So it's looking at it over a larger frequency spectrum, and then it's sampling what it sees there, and it's going to give you those results accurately and quickly. And it increases the probability of capturing impulse noise events. Increased flexibility in measurement and testing applications. So, view in-channel ingress on active carriers in the familiar frequency domain. So the thing is, even with DSP technology, you can even take, let's say that you have an area to where there's let's say this is where your modem carries at. We'll say your modem carries at 30 megahertz. With DSP technology, we have an ability of removing that modem carrier, so the only thing that's left is just the noise floor. So it makes it real good, because the thing is that as long as that modem carrier is there, if there's ingresses falling up under that carrier, you're not going to see it. So some more advantages of DSP: it captures impulse noise bursts, already identified as a major impairment to advanced services. Those impulse noises, things like I mentioned, coming from machine shops or transformers, equipment, equipment that is becoming faulty. Reduces service interruptions. It gives you faster alarm notifications, and simplified troubleshooting because of the DSP technology. And it gives the most accurate representation of the return path spectrum for when you're doing the certifications and when you're doing the reporting, because you need as much information as you can get so that you can quickly isolate and identify where the problems are coming from. In-band troubleshooting of active carriers. I mentioned that a little bit earlier, how the DSP technology, has the ability of removing system carriers from the display. The peak hole trace paints in-system carriers for reference, and then the live trace displays ingress levels inside the occupied band. Then the traffic mode, which is how I was saying that how you can look up under the modem carrier or under that traffic. The traffic mode can be transmitted to field units to localize and troubleshoot in-band interference. So not only will the NOC be able to see up under that modem carrier or the active areas, you could send that same display to your field units, and your field unit will see the same thing that the NOC is seeing. So it makes their troubleshooting a lot easier when the problem is that the modems are experiencing slow speeds, and we know that it's because some ingress is falling up under the carrier. You'll be able to see it, troubleshoot it all the way to the point of origin. So it has an extended frequency range, captures ingress under 5 megahertz. That's an area that's neglected sometimes, is that a lot of times we look from 5 to 42 and we say that, hey, that's it. But below 5 megahertz has a potentially powerful ingress from off-air sources. And it provides increased protection against laser clipping. So if that energy below 5 meg, happens to increase, and you can kind of see it from the illustration that I have on the screen there, how if you look at around 5 meg, how the level is extremely high. If you were ignoring that, or if you couldn't see it with your return path system, you would look at it and say that, oh, maybe it's not as bad as what it is, but your lasers are going to see it, because your lasers are going to go down to that particular range, and it's very possible that you could clip your lasers. So I talked a lot about the monitoring speed, or just the speed when using DSP. This gives an example of how a swept-tuned analyzer can miss some energy or impulses that comes through. In this particular test, we ran a test back at the Trilithic corporate lab, and what we did is we had a signal generator at 24 meg, and we had a pulse signal at 15 milliseconds. So a 15 millisecond pulse at 300 millisecond spacing. If you notice at the very top, there's three particular displays that's showing on the screen. The very top is using DSP. Now the DSP technology, which is what's in our SSTs in the head end, and that's the head end unit that's used to capture the ingress coming back on the return, that it consistently captured both the fundamental and the first harmonics. So those are things that most systems will miss. So preparing for return path monitoring. So this is typically what the network would look like when you're doing or setting up for return path monitoring. At the very bottom, we're going to start at the bottom. There's what's called the Viewer 2 server, sometimes called the Guardian 2 server. That server is what houses all of your traps. All of the traps are sent back there. It's the center point for both your head-end units, your client software that would be in your NOC centers and so on. So if you look at the very top left, it says the Viewer 2 clients. That's what would be in the NOC center, and your whether it's your supervisors, your maintenance crew, whomever that has access to the internet would be able to connect to the Viewer 2 server. And then they can look at live views of whatever's happening out in the plant. But then also it'll have the ability of receiving the alarms and things like that whenever a threshold has been violated. And then you have the head-end units, the SST 9581s. The SSTs is what actually looks at the ingress and monitors what's happening in the plant at all times, and you set up alarm thresholds so that if a level or if an alarm level is violated, that it sends back SNMP traps back to the server, and then you're able to view it. So the 9581 SST, it has different monitoring profiles. You can build up to 8 monitoring plans. So these 8 monitoring plans, would be used to monitor unique specs. So for service impairment, maintenance, engineering, you may have a one monitoring plan that is for, let's say if you have your areas broke up to where you have technicians that are maintenance techs that just works with the voice over IP. If you have like separate modem carriers, then maybe you want to send them a particular set of alarms that affects the voice over IP, and then another set that could go over to the high-speed data techs. Then you may have a set that is for the supervisor. They may want to see everything across the board. So you could have a profile that shows you everything. But then another type of profile that you could have set up is maybe you have a profile that is your goal, and then you have a profile of what it takes to get to that goal. So let's say if your goal is to from 5 to 42, that you don't want the noise to exceed, let's say you don't want it to exceed a minus 35, which that would be pretty good. So if that's what your goal is, but when you look at your node now that the best that you have is a minus 28, then what you don't want to do is that maybe you don't want to get a constant storm of alarms because you're not reaching the 35. Maybe you can have a working profile that maybe that particular tolerance is at a minus 31. So maybe that's a little more of a workable goal, and then once that goal is achieved, then you can move it to a minus 33, and then you can move it to a minus 35, and then it ultimately gets you to the goal. So you can do it in stages, but at least you have the ability of seeing both, that here's where my goal is and here's how close I am to my goal. And each profile can send SNMP traps to 8 different locations. So these particular traps can not just go to here, but if there's a different monitoring software, you could send those to different locations, and they could also be tracked separately. So your monitoring thresholds that I mentioned, how you could customize those individual profiles. Alarm threshold information is stored directly in the 9581 SST, which is the head-end unit. And it has 5 degrees of severity. For ingress levels, it's critical to warnings. For outages, there's a no signal warning. Persistent settings, to authenticate alarm conditions, and then the traffic curves identifies the frequency and amplitude of the carrier. So you can look at the display when you're looking at the different color lines that are there. Those are your different tiers of alarm of your alarm thresholds. So in this example, if you're looking at, there's the green, the yellow, the red, and so on. The first 4 that's right there, those are your different levels, and you can see it on the left to where it has the different color that corresponds with the lines. So you have a level 1, which a level 1 is usually an alarm that, if you're if you need to have everything at a minus 30, then if this gets to a minus 29, it hits a level 1, or yeah, it hits the level 1, and it sends out an alarm. But that's not enough to knock out the system. So you may decide that, well, level 1, I want to be aware that it's there, but I'm not necessarily going to roll a truck right away. But then when it hits a level 2, let's say if that setting is set at a minus 25, now we know that, okay, hey, now this is starting to get to more of a problem. So we need to start alerting the technicians that, man, something is happening out there. So when that alarm is tripped, it can, have a different degree of response. And then your level 3 could be that when it gets to this point, that is, we know that it can affect your performance. And then a level 4 could be that if it reaches that, you have customers that are calling in. And then your top to where it's it's kind of a teal color or a light blue. That's your traffic curve. So you can bring that traffic curve down into your modem burst, and whenever the modem burst does not cross that line, it will remove that from the screen. So the only thing that's left is just the noise floor. And then at the very bottom, you have a low limit, which you would set that just below your noise floor. So if your noise floor dropped below that line, then you would be able to say that node must be offline. So it sends you so it lets you know that there's an outage that's going on. So the tool that allows you to actually look at the curves, because everything that I showed you there is what's set up inside of the head-end equipment itself. Because remember, the head-end equipment, the SST, is going to send alarms from there to the server. Now this is the other piece, which is the Viewer 2 software. This is what actually looks at the server, or it looks at that information that was sent from the SST. So like I said, it provides the access to the Guardian 2 servers. It populates the Viewer 2 windows with node status trees, alarm incident logs. And it provides access to spectrum analysis tools, node alarm history, and alarm reporting modules. Now, Viewer 2 uses an interface. The components, it has a status tree. The incident log shows any of the incidents that were happening, any of your alarms that were sent. An alarm history, so it archives your alarms that were received. And then also a spectrum display that you can look at the live view of what's happening live, but then it also show you what your alarm when the noise violated that particular return, it'll capture that, and it'll show you what the alarm display looked like. So the node status tree is a graphic representation of alarm conditions, and it's defined according to the geography, the deployed services, and the management responsibilities. So what this can do is that if you're in a NOC center, you may oversee a couple of different or a few different cities, and then or a few different hubs. And then you also have your master head in, and then from your individual hubs, can go to different nodes. You want to see some type of tree that shows you each particular tier. So it includes free-form fields, like what was mentioned, from the for node locations, for sub counts. Defines grouping criteria for report generation. So you want this set up so when you print reports, like for example, if I'm the maintenance tech, I may only be concerned with just the problems that's coming out of the East Hub. But now, as the manager, I may want to see not just what's happening from the East Hub. I want to see what's happening from all of the hubs, and then so on. The VP of engineering may want to not just see what's happening in all of just the hubs that you're responsible for, but may wants to see what's happening in each of the other cities that's using the monitoring tool. So there's different levels that you want to set the tree at based off of what the response or what the area of responsibility is. So this shows you your node status tree. So if you notice in the example here, it says it shows that the first tier here is Palmdale. So Palmdale would be the overall, that would be the head end location, and then it goes to Acton, and Acton would be the town that it's going to, or that particular hub. And then under that hub, now you have all of the different nodes. So this kind of gives you a little bit of a breakdown of how you could set up your node trees. So you have your incident log. Now this displays current node alarm events based on the traps received by the Guardian 2 server. Now remember, the traps originate in the 9581 SST, and that's all based on the alarm threshold violations and the persistence settings. You know, how often you want to display an alarm. Displayed information is based on the status tree configuration, but it typically includes the node ID, the severity of the alarm, you know, which threshold, whether it was a level 1, level 2, the elapsed time, how long it was in an alarm state, and then the total alarm time that when it was in an actual alarm before it was actually the problem was actually corrected. And this, like I said, this is excellent for reporting. So managing the alarms, prioritize the alarm information. So your sorting tools organize alarm information into logical groupings for managing service interruptions. So it kind of shows in this particular display, it shows the return path ingress, and then it shows the node that it was actually going to, or where the problem was coming from, what level that it was, the alarm was received at. Like the top one was a level 4, which is, you know, pretty severe, and then it shows the duration that there was an alarm that it was in a level 4. But then it also says from the time that there was an actual level 4 alarm, you know, what's the time to date? From that particular time, how much time has passed before it was actually addressed or recognized? And then it shows the hub and the city that that particular node is tied to. Now, once you identify that you know, hey, there's a problem there, I corrected it. Now you will have ability of acknowledging that and saying that, hey, it's fixed now and it can be removed as an incident. So the alarm acknowledgement identifies which NOC operators are working alarm. Improve NOC efficiency. It quickly identifies who is working service interruptions, prevent duplication of effort, and manage a workload in the NOC environment. So from a NOC perspective, you're able to identify which areas needs the most attention. And then you can filter alarm events by knock operator. So reduces screen information, displays only operator acknowledged events, and unacknowledged events. So you can go through, let's say if you didn't, let's say you only wanted to see those issues that someone has actually did some repair, or no, let's say it the other way. Let's say that if someone has already accepted or acknowledged that this problem is going on, then you don't really need to send that out again. So maybe you want to just filter your screen so the only thing you see are those things that has not been acknowledged. And then for alarm filtering, the alarm filtering provides focus on most severe alarms. So you can select alarm severity. Temporarily removes alarms of lower severity from users' incident logs. So for example, if you know that the level 1 is not really a severe, it's not anything severe, but it's something that you just want to keep an eye on, then you may not want to show that if you have a lot of level 3s and a level 4 alarms. So what you could do is you could say, well, only show me from a level 2 and greater. So it kind of reduces the amount of stuff that shows on the screen, and then you know that the only stuff that you're seeing are the items that you're wanting to deploy a technician to go out and do repairs. So in hide incidents, after maintenance is dispatched, knock operators may hide the alarm events while service is restored. So this temporarily removes the alarm events from the incident log for whatever period of time that you set it up for. And then quick references of alarm events where service restoration is in process. So if you see here to where the hide incident is selected, I could just select it to hide it for 30 minutes, or maybe I want to hide it for 2 hours, or maybe even 4 hours. I know that it may be a bigger problem, so I'm going to give them more time to do the repairs. So your alarm troubleshooting. To investigate alarm conditions, the knock operators can click on alarm events in the incident log. When they click on the alarm events, it brings up the spectrum view. And in that particular spectrum view, it shows the alarm threshold and ingress signature that caused the alarm event. And it allows the operator to correlate alarm data from other monitoring sources. And it evaluate the effect of ingress on system services. So I can actually go through and by clicking on that, one is I can see what the when the alarm was violated, what the signature looked like, and then I can look at the live view and see if it's still looking like that now, or if it was something that was just a quick burst that came in and then it left. Then we can identify that pretty quickly, and that'll help us know what's the best time to deploy a technician to go out and repair the problem. Spectrum marker use. That allows the knock operators to identify the frequency and level of points of interest within that ingress signature. So in this particular, with Viewer 2, it has 2 markers which may be set to perform measurements on all ingress traces. For frequency and amplitude identification of ingress signatures. If you put it at 23 meg, and you know that that's where ham radios are at, you know that, okay, I need to be looking for areas around the ham radio towers, or if it's CPD, if I see that I have beats that are coming back every 6 megahertz, and I can say that, okay, man, that's looks like CPD, and I can alert the technician that's out there that that's what they need to look at. a comparative measurements between ingress level versus or level or slash frequency versus the service level or frequency. So it's what's happening right now opposed to what did happen. So stores changes in alarm states. So recall past alarm events correlates alarm events with service interruptions and identify ingress signatures for troubleshooting. See, so you notice now there's the knock operator that's looking at the monitoring tools has a huge opportunity to see the overall picture of the network and the ability to deploy the right person out to do the repairs quickly. Now, the folder size that is used in the setup window, the max folder size is 200 state changes. Limiting folder size speeds loading of the spectrum analysis tools. So that's the reason that we keep it at 200 events. So now that we've looked at the monitoring tools, now we need to be able to generate reports. So what we do is we print out or can have the ability of printing out node service reports. So returns alarm activity over user specified time, period, and locations. So it provides a correlation of service interruptions and return path ingress events, identifies and prioritizes nodes in needs of maintenance. It's kind of what I've been talking about. And the selection criteria, alarm severities or the number of nodes per location. Remember earlier in the webinar we were talking about certifications. This is a good way to certify. You can set up your certification for that 24-hour period, or you can set up for 7 days if you want. But you can look at what's happening over that period of time, and you can definitely feel confident by this type of reporting that if a customer was installed there, that they're going to have a decent service. So your node service report, the summary view of the report itself, and remember this is customizable. It includes the selection criteria, and it lists nodes meeting selection criteria. So it could be grouped by location, the number of nodes per location, or the top nodes that are having issues, and then the number of alarm events per location. Nodes by location lists nodes meeting selection criteria. Provides alarm counts per node. The elapsed alarm time broken down by the severity. And then the percentage of time the node was in an alarm state. Figure of merit information for tracking node performance. So it's just so important that these type of reports are viewed, because the customers, they're paying for this for a high level of service, and they expect a high level service quality. The node alarm detail list is a chronological list of alarm events. The severity, the frequency, or how often it's going into an alarm, and then the maximum power, the peak power of the alarm state. Gives a quick correlation between events and service interruptions, and spectral information may be obtained from node incident log. Alarm dispersion reflects alarm occurrences over time and severity. Identifies the optimum times for locating ingress events. Provides clues as possible origins of ingress. So this gives a lot of information based off of the severity of the alarms that are sent. Now, once the nodes are generated, now you want to give this to the proper people so that either repairs can be made or that that we can that the management team can verify that the network is clean or it's performing the way that it should. So you can both save and share reports in quite a few different formats. There's HTML, Excel. You can just do a web archive, PDF. If you don't want anything changed. The list goes on with different type of formats that can be exported or where your reports can be exported. So your node certification report automates node certification testing. It specifies locations and time span, and then it returns pass and fail results based on ingress levels versus the whatever your specified limits were set for. The summary report, it'll include the header information. So what is it actually? It's node cert report, summary of the test results, and then pass and fail results by the individual nodes. Now, also in the report, it'll give a spectral view. It'll give the maximum, the minimum, and average ingress spectra over reporting time periods, the pass or fail thresholds, and the pass or fail tolerance, the ratio in dB between the threshold and the ingress spectra. And you can kind of look how you have the multiple levels. What you're when you're looking at, there's three particular lines that's drawn on there. Your lower one would be what your actual minimum, what the minimum level was. Then you have the middle, which is the average. And then at the top would be your max, what the max level was. So now the thing is, now we talked a lot about the doing the monitoring and what the NOC centers are going to see, and then also doing a spectral view, from the NOC center. Now I want to just talk about ADIA, which stores or archives this particular information, and so that you have historical views that can be viewed at a later time, or that the field guys could use to assist them in their troubleshooting. So what is ADIA? What it is, it's an ingress analysis server. And it's specifically designed for convenient and efficient historical analysis, archives up to a year of data. It displays both historical and it shows live spectral views. It calculates the average probability that a node will exceed its thresholds over time. Recall spectral information over selected time periods. View frequency, availability of the return path for new service launches. It evaluates the impact of changes in modulation schemes on system services. And it verifies existing services are meeting performance standards. And then it can generate figure of merit calculations for return performance. See, with ADIA, it collects spectral information from the 9581 SST head-in units. And the spectral information will contain the maximum, minimum, and average ingress information collected in the 9581 SST, the head-in unit, and then it'll compress it into 15-minute summaries. Return path performance information against user-specified limits. Now this server provides database storage for 3,000 nodes over a 1-year time period. So I talked about the spectral history. So this is all looking at the ADIA view of this, because remember we looked at what the viewer 2 sees, which is looking at live. Now this is showing the archives and also a live view. So review ingress signatures of selected node over whatever specified time period. The max, the min, the average traces with the live spectral overlay. So if you look at the illustration on the right, you'll see three purple lines that's there. The lower line is the minimum level that happened in that 15-minute period, and then you have your the middle, which is the average of your peaks versus what your minimum levels were, and then you have your max trace. Under that, it shows your live view, what was happening live at that time. And then, so when you're looking at your axis, your y-axis on the left side, it gives you what the level was, what the intensity was. So if you're looking at this particular display, it shows that the minimum that was happening was at a minus 20. Well, it looks like it drops down to a minus 25, but it really looks like it's pretty much hovering at a minus 20. But then it showed that it was averaging at a minus 10. But then it showed that that it peaked as high as a 20, and this is all based off of what alarm threshold that you were wanting to look at. So the spectral history, it gives both a spectral and a time-based view, and it evaluates the severity and duration of ingress related events. And then you can also view the waterfall graph, which is at the bottom of the two displays there. What the waterfall graph is going to show you is it's based off of the particular frequencies. If you look at the axis on the left, or that y-axis, the vertical axis, it has 10, 20, 30, and 40. That's the frequency range. And then if you look at the very far right side, there's some color codes that shows amplitude. So if I know that my modem carriers are running at 30 meg, then I'm going to want to see what level is happening in that particular 30 megahertz band. So if I see in that particular 30 meg that it shows some orange, I can look at my key on the side and it can show that that's at 20 dB. Or if I'm looking at if it was around if you're looking at around 35 megahertz, it's blue. And on the side there, that particular scale says that the blue, depending on the intensity of the blue, it's at like a minus 30, minus 25, and so on. So it kind of gives you an idea over that particular time period which levels or which frequencies were having the most problems at a particular time, so that you know that if that's a good spot to put a modem carrier. So the last thing I'll mention on that is that if I wanted to see, based off of what I'm seeing on the lower waterfall graph, since I see a lot of blue between 30 and 40 megahertz, then if I was going to put a modem carrier or add another upstream carrier, I would say between 30 and 40 megahertz would be my best spot to put it. Now, if you look towards the bottom where it's around 10 megahertz and around 15 megahertz, there's a lot of color there. So I know I wouldn't want to put an upstream carrier there, because I know that I would have a lot of impairments. So it gives an ingress threshold probability, evaluates the return path spectrum for new service deployments. So this will identify the cleanest portions of the spectrum for new deployments, similar to what I was showing you on the waterfall graph. And then the metrics are displayed as percentages of unavailability versus 4 user-specified limits. So it lets you know, based off of the limits that you set up, what percentage of time was it violating that particular limit. So if it shows that it's violating that limit, 100% of the time, then I know that, man, there's a lot of problems. Or if it's at 50% of the time, same thing. But if I see that it only violated the limits, at 10% of the time, then that's something that, I may be willing to go with that because I can clean that. I could possibly clean that up. So then your over limit by frequency evaluates the availability of new services before deployment. It verifies current service availability, and then it studies the impact of changes in modulation format. So it's the same thing, gives you the percentage, and then based over time. The average unavailability is a figure of merit calculation for return path performance. So it compares ingress levels against 4 limits. So you can track the progress of return path maintenance efforts. So if you want to see if what the maintenance techs are doing in a particular node, if it's making a difference, then you can do a comparison analysis, and it'll show you, what actually happened based off of the limits that you set. Now it also gives a web portal or a web view. So it gives you real-time access to head-in ingress levels, the max, the min, and the average traces. And then it has the markers that's available. See, now this is a good tool for all of the maintenance techs to carry on their laptop, in their vehicles, because what they could do is that when they're making all of their repairs, if they want to see if that's making a difference, or if something's happening right, or what's happening right now inside of the head end, they could use their web portal, and it'll show them exactly what's happening in the head end right now. And then they could also toggle between the different nodes if they know that there are 3 nodes that are combined together on a particular blade. Then they might want to look at what's happening in the other node, because the other node could be what's affecting that particular display or that particular node. So then it gives a service report. So now, based off of your alarm levels, you could generate a report right there on site to see which one of your nodes are in an alarm state more, or in a particular alarm state more. So it'll show, how many level 1 alarms that you had in that particular node, and then you can drill down into that to see, wow, this may be this is a node that I need to work on for this particular day, because that's where I'm having the most problems at. So as a conclusion, adding services on the return can be a challenge, but if you have the right testing equipment and then having good procedures in place, you'll definitely succeed in keeping a good, clean return path. With Viewer 2, is what I mentioned, is the monitoring software. It empowers the NOC operators to manage and troubleshoot alarm events over large geographies and high node count densities. DSP technology provides the most accurate representation of return path noise and ingress levels. Troubleshoot in-channel ingress on active carriers. So if there are, if you have your modem carriers that are right there, you want to see what's happening up under that modem carrier, because that's what's going to impact that upstream modem. carrier. And then also the ability of having historical analysis. This allows engineering to anticipate impact on system services based on historical return path performances. Now, I know that there was a lot of information that was given, but it's some very useful information, because the thing is that the monitoring is the backbone. That's what's going to allow you to be in front of the curve. It's going to allow you to anticipate problems before the customer has to call in and tell you that there's a problem. I'll now respond to any of the chatted questions that were sent. All right. Some of the questions that came about. Let me see if I can expand out on this a little bit. First of all, you do see on the screen for specific questions about doing whichever type of monitoring that you're currently doing. Feel free to. You can send me an email directly at tholmes@trilithic.com, or you can use the support email, the support@trilithic.com as well, and that can get you directly into the support team here, and there's also a 1-800 number. The one question was, why is the bottom of the noise floor at -20 and not a -40? I'm not sure exactly which display that's referring to. But just so you know that that I would expect the noise floor to be around a -40, a -30. It's possible that that particular screen that you were looking at was just here in the test lab, not actually a real life active node. So the noise floor may have been a little bit higher than what you would ordinarily see. But you're spot on that you would have expected to see that noise floor around -40, -35, somewhere in that neighborhood. Then I have a question: how many nodes can this software SST manage? As we have 29 nodes total, as they're using a different type of sweep gear or monitoring gear for sweeping now, and the 860s for level 1 techs. Actually, that question in general, that may be a better question to contact me direct, because I'd like to get a little more information from you, so that I can understand exactly what you're actually wanting to see on that, or what's the actual thing. But depending on the number of SSTs, or the equipment that's looking at the nodes, will determine how many nodes can actually be monitored. So you can actually have that up to quite a few nodes. As far as storage space on the actual server itself, it'll support, for 1 year's worth of data, it's about 3,000 nodes. So hopefully that answers the question, but feel free to shoot me an email at tholmes@trilithic.com, and I can get a little more specific on that. All right. Then it talks about the upstream SNR, correctable and uncorrectable errors, but is not efficient enough to isolate the problems, as multiple nodes are combined per the RF port. So majority of the time it uses a spectrum analyzer in the head end. Yes, why don't you go ahead and contact me again offline on that, Tim, as well, and then we can talk a little bit further about how this actually captures the ingress, and some of the best ways to where you're able to look at the actual noise that's in the plant, and not combine node from the equipment, especially if you're not doing a one-to-one port combining. Then just because of the multiple nodes that's combined together, the total noise floor will be elevated as well. So there's some little rules of thumb that you need to use in those particular incidents. The last thing is This particular presentation, it will be available online. If you do want a copy of that, you can go to our Trilithic website, and all of our links, not just for this presentation, but all the ones that we've done in the past, there's a spot on the website under the broadband instruments that takes you into the recorder, or to the previous trainings, and then also this one here, or you can contact me directly, and or send an email to me directly, and I can get a link to you once it's processed. It takes a little bit of time to get it processed, but once that's complete, I can get that over to you. All right. Well, I appreciate everybody joining in. We're actually planning on having another presentation a week from Friday, covering something. I cannot remember what it's. Voice over IP. It'll be covering voice over IP, so it's going to go into some different testing for that, and then we're going to have one the week after that with digital troubleshooting. So continue to look at our website, and it'll give you a lot of information as far as upcoming webinars. All right. Thank you.